So in the previous class, we were solving a problem that is a conversion of the given mechanical system into its equivalent network, and we are trying to write the differential equation notation, right, based on the what kind of blocks that particular system has. And we had identified two nodes because there are two different displacements x1 and x2 corresponding to the two masses m1 and m2, and then we had written the equations at both the locations, correct? So till there we had done. Now in the next step, our intention here is to find the transfer function. That's the overall question here, right? So in order to identify the transfer function, we have to proceed in the following fashion. Okay, so first let's try to write the Laplace. Let's take the Laplace transform on both sides for both the equations. All right, so that is okay. Let's write for the first one. Okay, so that is taking Laplace transform on both sides. So the first one is m1 into d square x1 by dt square. X1 indicates that x1 is in terms of time. Okay, it's x1 of t, right? So x1 of t has a Laplace transform x1 of s, right? So the domain changes whenever we apply a transform. So time domain is going to be replaced by its equivalent s domain. All right, so the constants will remain as it is. So this is m1 as it is. So uh, we are applying the following rule, that is, if you have, so there is a specific property in Laplace. So that is, if say x1 of t has the Laplace transform, that is x1 of s. Do you remember what happens when d square of x1 of t over dt square has, right? If I differentiate the function on time domain, what happens on the on the s domain? If you remember, the one differentiation multiplies an s over there. Okay, so double differentiation gives you s squared, right? So since I'm differentiating twice, I'm multiplying by s square. Okay, so this is s square into x1 of s. This is the property that we are going to use, right? If you have a single term, right, then the single, if you have a single what do you call differentiation, that is dx1 by dt, it is s into x1 of s, right? So according to that, now I'm going to write, let's go back and check the equation. So m into dx1, so d square, so this is s square into x1 of s, first term. Second term is b1 into s into x1 of s plus k1 into x1 of s. There is no differentiation, so simply x1 of t becomes x1 of s. All right, so then we have plus, so I can write this is k2 into x1 of s minus k2 into x2 of s becomes equal to f of t becomes capital F of s, because f of s is also a function of time. We can write it this way. Separate the terms containing x1 and x2. So to simplify, I can rewrite this as, this is m1 s square plus this is b1 s plus k1 plus k2 into x1 of s. plus, sorry, it's minus. Okay, the last term is negative, minus the k2 into x2 of s is equal to f of s. So call this as equation number one. So we also have to apply the Laplace transform for the second equation. So if you okay, let's write the Laplace for this the equation that we had written at node x2. So that is m2 into s squared x2 of s, correct? So plus this is k2 into x2 of s minus k2 into x1 of s is equal to 0, right? So fine, this is equation number 2. Now if we want to uh, okay, now can you suggest any method? Anyway, we applied the Laplace, right? Can you suggest a method so that we can find out the specific ratio? The ratio is which ratio we want to find. It's a the question is to find the transfer function. So the output by input is what we want. uh, Output is considered as the variable that is present at the at the output, the last output, that's considered as x2. X2 is the final uh, response of the system, and the input is f. So we want the transfer function x2 by f, right? It can be found even in the Laplace domain or the time domain, anything is fine. Since we have taken the Laplace was taken because it's easier. Okay, so this technique is easier than computing the transfer function in terms of the time domain, right? Anyway, we are halfway through, but next step, what could be the next step so that you can find out the transfer function specifically? So I'll highlight. So this divided by this is what, sorry, x2 by f is what we want, right? In the sense, I need to eliminate this from that equation, first equation. Still fraction possible? Yes, yes, yes. Yes, we don't have to solve it as of now. Okay, so we need to find a ratio, right? So the anyway, multiple methods do exist. Second equation we cannot directly use because there is no f of s here, right? So you have to go with the first equation, but I have to bring the second equation in the first equation in some sense. Okay, so one option is that it's easier. You can see that you can get the equation of x1 of s, right? Get the equation of x1 of s from equation number 2 and put that x1 over here, right? So you get the whole equation in terms of x2 only. So that x2 is also present over here. You can take the x2 common, right? And we can proceed further. That's one method. Okay, so but I will suggest another method. Okay, so the second method is by using the matrix representation. So convert these two equations, equation 1 and equation 2, can be represented in the matrix form first, because matrix suggests, because if at all in this case they just asked what is the transfer function, that is x2 by f. But if at all they also ask the f x1 by f possible, right? Then that method, whichever is I told first, right, that's going to be tedious because you have to repeat the same thing, represent the whole x1 in terms of x2. That's the first step. In the next case, you will represent every x2 by x1. You modify the same equations and then substitute back, then further simplify. Okay, so that is not suggested when multiple questions are asked of the same type. If it only one question, like only find the transfer function, fine, you can do that. But if many other ratios have been asked, right, then I suggest to go to the this one. Okay, the matrix method. So right, so put equation 1 and equation number 2 in matrix form. So it means the coefficients of x1 will come in the first column, coefficients of x2 of s will come along the second column, and so on. Okay, so I can see that in the first equation, coefficient of x1 of s is this, is m, yeah, so m1 s squared plus b1s plus k1 plus k2. Okay, so this is the first thing. And the coefficient of x2 in the first equation comes in the second column, that is minus k2. Okay, let's go to the next equation and write the coefficient of x1 first, because I started with the x1. Right, we have to stick to the same thing. Either I write only x1 first, x2 next, or the reverse. Okay, so since I wrote the x1 first, I'll write the coefficient of x1 from the second equation, that is minus k2. Right, because that's here. The coefficient of x2, anyway, I had not simplified over there, but anyway, I'll club it and write it. So this is m2 s squared plus k2, correct? So that's from here. All right, so this is the matrix corresponding to this. Now what are the variables? Variables are written in the second equation. It's a, you are trying to write a linear equation, ax equal to b. This is x1 of s and say x2 of s is equal to, write the RHS. So for the first equation I have f of s, for the second equation it's 0. So we'll call this as equation number 3. Now if you remember the simplification or solving the matrix equation, right, I can try to find out the value of x2, right, but that x2 will definitely use this and this matrix. So the matrix has no f or this thing, right, but f will be used to calculate that. That's why we try to represent this. Now let us see, uh, how do you find out x2? X2 can be found by replacing the second column of the matrix with the this thing, correct, and dividing by the determinant of the given matrix. So this is what I will write. So let's try to write it in this way. So that is okay, let's try to find the determinant. Determinant, say delta is equal to, this is multiplication of this minus this, right? So that is m1 s squared plus b1s plus k1 plus k2 into, this is m2 s squared plus k2, this is minus k2 squared. This is the determinant. Okay, now if I want to write x2 of s, this has to be, now you see that now we bring the f of s into inside the determinant, right? Just so I will write, that is, maybe this is maybe this is second value, so I'll write a delta 2 by delta. So if at all they asked, right, the relationship between x1 and f, what you will do, you will replace f to the first column, replace this whole thing by the f of s and 0, call it as a delta 1 by delta. True. Yes. Now the first variable, so first, sorry, second variable, so second column we are doing now. If at all first, then the first column. All right. Okay. So delta 2 is what I'm supposed to find. The delta 2 can be calculated like this. So the first column remains unchanged. So there is no change. So let's start with the m. Okay. So this is m1 s squared plus b1 into s plus k1 plus k2 and minus k2 over here. So this is f of s and 0. This determinant I need to take all divided by the delta value. Delta is already right, we have calculated. That means, so what is the delta 2 now? Delta 2 is nothing but it's a 0 plus k2 into f of s, right? K2 into f of s divided by delta. This is x2 of s, right? So the question now, therefore, the transfer function is equal to, in this case, this is x2 of s divided by f of s, right? So how do you calculate that? Bring the f of s to this side, right? It's just k2 by delta, right? So that is k2 divided by delta. So the delta value anyway we have already, so simply we can substitute over there to get the answer in the final form. Right. So this delta value we can substitute here to get the final answer. Okay, so just go through this answer once and let me know if you have any doubt. Fine, right? Okay, right. Now we need to solve another problem that's based on the rotational. Okay, so linear is fine, right? So any problem you can solve using this technique. Let's say that the question is okay. Let's say the question. There is G1, so you can have theta 1, K1, J2, theta 2, and K2. So let's say that the question I'll slightly modify it. Now we will, so when t is the input, right? Theta 1 and theta 2 are the different outputs, and normally if the simple question could be something like find the transfer function, then I'm supposed to find theta 2 by capital T. Theta 2 by capital T. T is the input, theta 1 and theta 2 are the outputs. Okay, so output by input. If at all the question can be changed like this, now I'll change the question. So find, say, theta 1 by capital T. This is the question, right? So, right, again, I can apply any of the available techniques to solve. So first objective, yes, it has to be in that form. So preferably, we can go with the Laplace. All right. First, we can simply write the differential equation, and then we can write it. All right. So very similar to the previous question. Now our objective is to write the network first. So yeah, we are finding the theta one and sorry, we are finding the equations first, differential equations first. and then we are writing this. So you see that we had a question, we wrote a network. In the network, we'll identify what are the nodes. At each of the node, you write equations, convert the equations into Laplace, then you solve. Okay, so this is the same approach, but the question is now for the rotational network. Yes, correct. So first we'll identify the nodes, right? Like the previous case where you had displacement, now you have theta 1. So every location where you find a theta 1 will be a node. Node, this is another node. So whatever is connected to theta 1, you will be writing over. So theta 1 is only connected to J1. So J1 is here between theta 1 and reference. So between theta 1 and theta 2, I have K1. Theta 2, it's actually even you if you write a theta 2 here doesn't matter, because for a J, theta 1 and theta, there is no difference between the thetas, right? So on the both sides of J will rotate in the same fashion, like a mass. Both sides of the masses will travel by the same distance, right? So because of that, so even if theta 2 you shift to this side, no problem, absolutely fine. Okay, so the J2 is actually connected only to theta 2. All right. So this is the J2. And you see the theta 2 is also connected to K2. It's not between K2 is not between theta 2 and theta 1. So yes, so reference means it's ground, right? So actually this in an electric network, this could be the ground. All right. Fine. Now where the input is connected, that also I need to mark. So I'll connect this as input to this. All right. So this is capital T. K2. This is say K1. Once the given problem is converted into the network, right, the problem becomes very simple. Now let's write the equations at both nodes. So the first part is at node theta 1. Okay, so at node this, so J1, I can see a J1, so this is J1 d square theta 1 by dt square, right? Then theta 1 is also connected to a K1, and the response of the K1 is difference of theta. So this is theta 1 minus theta 2, right? This is equal to whether any input is provided to this node, yes, that is capital T. Now, similarly, at the node theta 2, what happens? We'll see that J2 is connected. So when we have J2, this is J2 T square. We have K2, K2 into simply theta 2. Then we have the K1, 2 minus theta 1 equals to no input on that side, so this is equal to 0. Okay, so all this is 1 and this is 2. Now to take the Laplace transform of both 1 and 2, that means I have the first equation becoming, this is J1 into S square into theta 1 of S. So originally the theta 1 and theta 2 are functions of time. Now they are transformed into the S domain. Okay, so plus we have k1 into theta 1 of s minus the k1 theta 2 of s equal to t of s. Actually, the t which is written in equation 1 is a function of time, right? Now that this got converted into the Laplace s domain. So let's club the terms containing theta 1 and theta 2 separately. So that is j1 s squared plus k1 times theta 1 of s, j1 s squared plus k1, yes, minus this is just k1 times theta 2 of s is equal to t of s. Say this is equation number 3. Similarly, let's take the Laplace of the equation number 2. So that is, I think we have with j2 s squared theta 2 of s plus k2 into theta 2 of s plus k1 times theta 2 minus theta 1 equals to 0. So we club theta 2 of s, sorry, I think I have to write s over there. So I write in this way. So this is k1 into theta 2 of s minus k1 into theta 1 of s is equal to 0. Now let's separate and write the terms containing theta 1 and theta 2. I prefer writing the theta 1 first. Okay, so this is minus k1 times theta 1 of s plus j2 s squared plus k1 plus k2 into theta 2 of s equals to 0. So call this as equation number 4. Now we can directly convert equation 3 and 4 into matrix. Equation 3 and equation 4 in matrix format. So that means j1 s squared plus k1, and this is minus k1. We have minus k1. This is j2 s squared plus k1 plus k2. Multiply this with theta 1 of s be equal to the first and 0. Now just find out what you want. Since the question is to find theta 1, right? So we'll find the determinant first. So determinant delta should be equal to j1 s squared plus k1 into this is j2 s squared plus k1 plus k2 minus k1 squared. All right. So next part, if we want to find say theta 1 of s, this has to be I'll write say delta 1 by delta. So delta 1 is nothing but replacement of the matrix by the first column of the matrix has to be replaced by the right hand side. So that is of s minus k1. This is 0 and j2 s squared plus k1 plus k2. Its determinant is this is delta 1 whole divided by delta. Okay, so this is j2 s squared plus k1 plus k2 into t of s whole divided by delta is the theta 1. The function which they have asked is theta 1 by ts. Correct? So that therefore theta 1 by capital T of s is equal to j2s squared plus k1 plus k2 divided by delta. Alright? Now, fine. Like this, you can solve for any mechanical system based block diagrams can be converted into its equivalent differential equations, and you can find the transfer functions easily. Alright. So the next objective is to find the equivalent component of a mechanical system in terms of an electrical system. All right, so that concept is called as analogous circuits. We have to find what are the equivalents, okay, of a given uh, mechanical component in terms of electrical. So for the first thing is, let's consider a system like this. It's a mechanical system. So let's say that we have a reference. So there is a spring, there is a damper connected to a mass. This is M, this is K, and this is B. And let's assume that we are providing an input to this. Okay, this is f of t, and we know that this is going to generate an output which is x of t. Okay, now directly convert this into the network. All right, so I'll write the network here. So I see only one displacement, so simply you can write this is x of t. Okay, all right. So one node now, only single node. It is just because uh, only one displacement. So to this displacement, I can see what are the components connected. All the three components are connected to same, right? So there is spring, so there is mass, and there is a damper. Three connected to the same, and you are providing the input to this. Correct? Okay. So this is the f of t. So this is spring K, mass M, damper B connected to this. Okay. Now the next objective is I want to find the equivalent of electric, right? Any electrical component. Basically, basic electrical components are capacitors, inductors, and resistors, right? And the power supply could be, in the sense here f of t is yeah, the input. In case of an electric circuit, the input could be in terms of voltage, where you have a voltage source. Current could be the input, because you can even have the current source as input. Okay, so considering that, now I need to think of an electric circuit which looks similar to this. Could be, right? Could be something like I can read it. Okay, before writing electric circuit, let's write an equation first. All right. So at node x for the given network, let's try to write an equation. Okay. So what should be the equation, right? It is the m into d square x of t by dt square plus b into dx of t by dt plus k into x of t should be equal to the input, that is f of t, isn't it? Now we need to think of something, right, where I can convert this into an equivalent electric circuit, right? So the electric circuit what we consider now is a parallel RLC circuit, right? Because I can see that something input comes, if I replace this input f of t by current, right, and I replace the three components by R, L and C. We don't know which one is equivalent to which component here, but we can still write an analogous circuit first, right? So we assume, we consider parallel R, L, C circuit. So that is, let's say the power supply is in terms of a current. All right. So only because parallel circuits are always considering current as inputs. We know that, right? So there is a R, there is an inductor L, and a capacitor C. It's a, it looks like an equivalent for us now. So we have an input, that is I of t as input. You can see there is a resistor R, inductor L, capacitance C. Now let's try to write an equation for this now, right? So it has to be what? It has to be the KCL, current, Kirchhoff's current law, right? At a particular point, right? Because this point could be your V of t, voltage. So I'm going to replace it as E of t because some reason, because I'm going to bring the V over there in the equation number 1. So I don't want to write a V once again here. So because here the X I'm going to replace as V of t, which is the velocity. Okay. So that V and the other V which we are going to write now, I don't want to get confused. All right. So I'm writing E here. Otherwise, actually this means a voltage. Okay, so depending upon the I of t, you have E of t changing across each of the device. All right, so let's write the equation now. So input, that is input is I of t. Input current is the current entering equal to current leaving the node. So what is the current leaving the node E of t through R? How do you find out? My question is, what is the current flowing through resistor? You know the voltage, you know the resistance, right? Yes, so Ohm's law is voltage by resistance, right? So that is simply E of t divided by R plus, it's actually sum of current entering equal to sum of the currents leaving. So there is a leaving current through an inductor L. So what is the equation for current leaving the inductor? Again, it's actually the Ohm's law only, but applied in a different way for an inductor, right? So for an inductor, the current through an inductor is given by, it is 1 by L integral 0 to till that time 0 to t, the voltage across that device, that is E of t dt. Okay, plus the next term through the capacitor, right? Capacitor is C into dv by dt, so this is d E of t by dt. Okay, so this is equation number 2. But if you want to make or if you want to make a comparison between equation number 1 and equation number 2, right, then this is fine. I can say that force is equal to current, right? But uh, I cannot, because the first equation is in terms of a, it's of the differentiation is of order 2. I don't see a differentiation of order 2 in this equation. So the left hand sides I cannot, right? I cannot equate. So for that reason, what I do, I make a modification in equation number 1. So that is uh, the x of t, right? I'll try to write in terms of the velocity. Okay, so that means so why I write, you understood, right? Because they cannot be compared, that's all. right? So now since the v of, okay, I'll write a velocity. Since velocity v of t is equal to dx by dt in equation number 1. All right, I'm going to make this change. So this implies, now let's see what happens. So wherever I see dx by dt, I write v of t. So d square x of t by dt square will become what? Alright, so dx by dt is this. So this implies if you have d square, okay, so if you have d square x by dt square, this should be what? This should be simply dv by dt, correct? Rate of change of velocity. And also there is a term simply x now, right? You can see that there is a term x in the equation number 1. Sorry, where is it? It's here. So how do you write x in terms of v now? I need x in terms of v. Take this. So x is equal to integral of v of t dt. So these three modifications I have to do in equation number 1. So this means now equation number 1 becomes, right? So the first term was m into d square x by dt square, which simply becomes m into d square x is dv by dt. So m into dv by dt. Second term plus this is b into dx by dt, but dx by dt is v of t. Okay, so I'll write v of t. So let me write this also v of t. So plus there is a k into, so k into its x, but x is nothing but integral 0 to t v of t dt is equal to, right hand side no change, that is normal f of t. Equation 3. Now 3 and 2 are of the same order. You can see that we converted the second order differential equation into the first order equation. So both are the first orders, right? Now the terms can be compared, right? So comparing, so 2 and 3, right? Equation number 2 and equation 3 we compare so that we identify various components which are equal, right? That we come to know is this current I is equal to this F, right? So I'll write the first term which are equivalent. Correct. Yes. So force in electrical system becomes equal to current in the force in the mechanical system becomes equal to current in the electrical system. Right. Then let's have the comparison of the other terms now. So whatever is this with M, you have dV by dt, right? So there is a capacitor C which has dE by dt. So okay, before that let's equate the term content. Okay, there is a velocity. Velocity will be equal to voltage, correct? Something into V of t. So something into E of t. So that's why we say that they are equal. So if you have the velocity, then it will change. Then it will, yes. So that will come next. Yes. We have a different equations. We have to write separate equations for them. Then we compare. Okay, right. So now actually there are two different names given. So this kind of analysis is called as the force current analogy. So force is replaced with the current. Okay, so this is V of t is equivalent to this, and that suggests that when you have the mass on one side, it becomes equivalent to the capacitance. And also right? We'll write the other term. I can see that P is equivalent to 1 by resistance, okay, and K is equivalent to 1 by L. Okay, so these are the equivalents which we can derive from this particular kind of network. Okay, just compare and our next objective is to write the different analogy where we try to equate the force with the voltage. Okay, so here I write in bracket, this is called as F force current, Fi analogy. Equivalent is very simple. We will consider a different circuit. Okay, so consider the series RLC circuit instead of the parallel circuit. Okay, so previously we directly wrote consider parallel RLC circuit, right? So instead of that, I am directly writing a series circuit. So in that case, we know that the series R and just what is a supply? Supply should be a voltage, right? Right. So it has to be a voltage now. So this is E of t and R, L, and C. So we assume that there is a current that is I of t in this direction, assuming this is plus minus. Okay. Now this means what should be the uh, response of the system in terms of the how do you relate the voltage and the current, right? So input the it's actually KVL. You will apply KVL, algebraic sum of voltages around a loop equal to zero, or the uh, voltage input voltage is equal to the response voltages, right? So input is E of t should be equal to what is the voltage across resistor. Voltage across resistor is again Ohm's law, I into R, right? So this is R into I of t plus what is the voltage across a inductor? Voltage across inductor is L into differentiation of the current di of t by dt plus the voltage across a capacitor is 1 by C times integral 0 to t, it is the integration of current I of t dt. Right? So let me call this equation as equation number 2, so this is 4, right? Once again I'll copy the equation number 3, right, because it's already in the required format, right? So right, yes, just have to compare and write the equivalent. Now, so let's simply try to compare them. So the f of t becomes equal to E of t, which is a voltage. So force is equal to voltage, and I can see the m into dv by dt. M is now equivalent to this. So whatever voltage, sorry, earlier there was v of t, which is the velocity, right, becomes equal to current now. So on, we can equate them in this fashion. So like that we can write the equivalent. So let's directly write the equivalent comparing, right? uh, 3 you compare with 4, right? When we do so, we get the force f of t is equivalent to the voltage. That's why this is called as FV analogy. Velocity on one side becomes equal to the current on the other side, I of t, right? You have m, which is a mass, L, inductance, okay? And I can see that the B damping coefficient is similar to the resistance on the circuit, okay? And the spring constant becomes equal to 1 by capacitance. We have two techniques to write the equivalent, right? The normal questions could be, we'll solve one problem on both sides. So one problem based on the conversion of a mechanical system into force current technique, and another mechanical system will convert that into force voltage. Two problems to come up in the next class.